Okay, so I'll start with what is meant by a data cube. I think it's important that everybody understand the method behind all of this, and what when we talk about the African Regional Data Cube, what is it really representing? So the traditional way of dealing with satellite data is we would take thousands of Landsat images over a time period, and we might use those images independently. We might try to stack them up and use them. And dealing with images that are spaced all over the country and in time becomes rather complex, knowing where those images are, what they cover, what they don't cover, and with borders and edges. Well, if we were to take the pixels out of those images and pull them out, and these pixels are 30-meter square pixels, we put them into a product we call a data cube. Now, we build up this data cube with smaller storage units. So what we do is we take 1 degree by 1 degree by 1 year. That's an arbitrary thing, but it allows us to stack up these pixels into these little building blocks and create what we call a cube for your country. So all that data is processed and ready to go. We actually have some advantages of compressing that data to make it smaller. But in the end, in the background, you have all of the information from the satellite images in a better condition and easier to process. So the reason we need these data cubes is that it makes it a much easier process for us to compile the data, and it reduces our preparation time. It allows us to query this data in time and space. Everything we're doing with this Open Data Cube project is truly free and open source software and algorithms. None of this is fee-based at all. The only thing associated with a cost is the cost of hosting this, and for now we have that in an Amazon Web Services thanks to donation from Amazon, but in the future there'll be other methods for hosting. Is it possible to mute on your end? It's still a bit of, I'm getting a bunch of feedback. Yeah, could you mute on your side?
Okay, continue.
Okay. And we're using the community to help develop a lot of these tools and algorithms. And so we're not the only ones doing this, and we're hoping that a broader community will continue to contribute to all of this. Once we stack all this data together, it becomes rather efficient, and it allows us to do time series analyses. It allows us to use multiple data sets. And in the end, we know it works. We've seen it work really nicely in Australia and more recently Switzerland. They've shown some amazing products out of this, and so we know the capability exists, and it's our job now to find better ways to get it in the hands of other people around the world like yourself. So here's where we are now. We have a lot of data cubes around the world that are under development, a number of countries that have expressed interest, and you see the 5 green boxes in the sub-Saharan Africa that are part of your African Regional Data Cube. So we have 9 operational cubes right now. We've got 14 more under development that'll be operational soon. So things are moving quite rapidly, and we have a significant amount of interest around the world, so it's exciting to see. Exciting to know that you're also on the cutting edge, and the African Regional Data Cube being a prototype is teaching us an awful lot about how to best operate all of this. So many times as we go through this, I have to urge that we're still learning. We're still learning how to best use all of this, how to make it better for you, how to make it easier on our side, and that's all part of the process. So once we have these data cubes in place, we now have the ability to use them in many ways for a number of algorithms. So here are some examples here, and some of these I'll be showing you in the next couple days. So cloud-free mosaics are a method to sift out the clouds out of all of the stack of imagery. And so we've got methods like the most recent pixel, median, geomedian, maximum vegetation. There's a number of ways that we can sift it out and sift out the clouds. Spectral indices, that I'll show you a number of these tomorrow, but you have standard vegetation indices, you have a snow index, a water index, fractional cover, tassel cap. There's a number of things you can do with spectral indices. We have methods to classify land using k-means random forest. I'm going to show you a water algorithm today, which is called WAFS from Australia, and total suspended matter, which is an approach for, it's a rather coarse approach, but it's a way to look at water quality. And then finally, land change. We have a number of land change algorithms. None of the land change algorithms are available in the user interface because they are a bit more complex and take quite a bit more to run. I'm going to just, I'm still getting a lot of feedback here. Let me just mute you temporarily. I'll unmute you in a moment when we get near the end. I don't know if anybody else had heard similar feedback. So the African Regional Data Cube was launched back in May for the 5 countries. We have a Landsat in the cube now. We're working very hard to add in Sentinel-1, Sentinel-2, and ALOS data. I say it's coming soon. I truly hope within 1 to 2 months we will have it in there, probably early 2019 at the worst. And certainly we want to update your Landsat data so that you have the most current data in there as well. We're trying to do this on our own. We don't really have a support team that is out there routinely working on this, but as we move forward, we're hoping to get some more support for you so that this is more automated. So right now it's our team. I'm NASA, and I have a team here of analytical mechanics, of folks that work with me, so you can consider us the NASA team in CEOS. And then Amazon has donated some cloud services. GPSTD continues to help with management support and training. We've done a number of web-based remote trainings like we're doing today. Other than the one visit we had in May, we have not been back, but it's possible in 2019 we'll have the opportunity to visit again. So hopefully we can make all of that work and you'll get some more face-to-face support. So since May, there's been a number of interactions with countries through this training and through other ways where we've focused on algorithms and use cases. So we've been looking at a number of products: agriculture, flooding, urbanization, deforestation and rangelands, specific to your country. Illegal mining has been an issue in Ghana and Sierra Leone. And so all of this is quite exciting, and we're hoping to continue to work with you so that you know how to make all these products on your own. So now I'm going to show you and walk through a number of these products so that you can see what they look like in the end, and what can be achieved with the user interface and with notebooks. This particular product here can be done with a user interface, and I'll be demonstrating this today. So this is water extent. This example here is over Lake Chad in Cameroon, Africa. And so what this product does is you specify a time window and specify a spatial region. And in this case, it's 17 years over a portion of Lake Chad. And what it's doing is it's analyzing every pixel in the stack of time in 17 years, and it's calculating the percent of time that those pixels are water. So anything that is dark blue will be water nearly 100% of the time. Areas that are red or yellow are infrequent water. And if you see the areas there in red, very, very infrequent, possibly only one time in 17 years. And I'll show you some interesting examples of that. Here is a product that we most recently just developed. This only runs in a Jupyter notebook, a Python notebook. It does not run in the user interface module. It's a little bit more complex at this point. Eventually, we might adapt it to run in the user interface tool. But what you're looking at here is Lake Salunga in Tanzania. And so this is an estimate of water extent, or measuring of water extent, for 4-year time period from 2014 to 2018. So what it shows is, as you move through time, some areas will change and the water will remain the same, which is what you see in blue. Areas in green have gone from no water to water, so those have increased in water. And then the areas in red have decreased, or the water has receded from this lake. And so part of what is done in the Sustainable Development Goal, if you're familiar with the United Nations Sustainable Development Goals, 6.6.1 talks about a methodology for evaluating water extent over time and determining the net loss in water and deciding whether that is considered a significant change, or perhaps, as it is in this case, an unmodified natural change because it's relatively small. And so you see here in the 4 years on Lake Salunga, there have been a few changes, but the total change, or the net loss in that water, is only 3.8% as a net loss in total water volume. And so it's interesting to see this example. So this is an animation. We now have a Jupyter notebook that gives an animation of the time series water extent. And what this is doing is it's showing the relative change in the water depth in Lake Salunga. And so if you think about, as water changes and goes from extreme heights and dries out over time to lower volumes, you are able to back out the bathymetry, or the bottom of the lake, and get an idea of what does the interior of that lake, or the bathymetry, look like, because you can do that based on knowing what the spatial area is as the lake moves in time and recedes. And so this is a really interesting animation. And what it's showing is, in periods of time, you can see there in 2016, where Lake Salunga was full, and yet in later, so there's December, now we're going to 2017, the lake is receding. And then in late 2017, it almost completely receded. So there's a large amount of change here in this lake. And what this does is this animation starts to show you the size and complexity of the changes in the lake. Are there any questions out there at this point? All right.
Any question?
Any other questions? I heard someone possibly trying to join in. So Majuni on the web, if you're not speaking, if you could all mute your microphones, it makes it much less feedback. Super, thank you so much. So I'll move forward.
Yeah.
Let me get back to where I was. Okay, so just yesterday, I ran this case for Lake Manyara in Tanzania, and I will show you how to do similar analyses on your own. And this is something I put together. It probably took me 30 minutes or more, maybe an hour of time to run through these various cases, capture these products. So, these things don't run in a matter of seconds. They might take a few minutes to run, and then I compile the results and start to look at various combinations. But what I wanted to show you here is that what has happened with Lake Manyara over time and how it experienced a drought in about the 2005 time period that almost completely dried up the lake. So what you see, this is a view of the lake extent. Remember, areas in dark blue are water that has existed the entire year. So I did yearly segments here. Areas in yellow or green are periodic water during the year. They're not water all the time. And so what you see in 2002, you see a fairly steady lake, a little bit of variation along the north, but a very large, steady lake. And you don't get any of these lines going through the data because in 2002, the Landsat satellite was running perfectly. And at about 2003, 2004, they ran into an issue with the instrument, so you get some streaks. So this is an artifact of the instrument. It's something we just have to deal with, and basically what it does is you lose a little bit of data. Now notice what happens in 2005. In 2005, the lake extent is much smaller, and it's yellow and green, which means this was not water except for a small portion of the year, maybe only a month or two of the year. The only part of the lake that was permanent the entire time is this little piece in the north. So 2005 was a severe drought condition in Lake Manyara. And what's interesting to see is 2 years later in 2007, it completely recovered. And you're back to where it was pre-2005. And now you can see actually in 2016, one of the more recent images, that the lake itself is rather healthy. It's even larger probably than it was in 2002. And you're actually seeing some areas here where you get some periodic water in the northeast region. So these are the kind of analyses that can be done looking at the historical changes in this lake and what years all of this has occurred. So now let's look at the same lake, Lake Manyara, but let's look at water quality. I found the results here to be really interesting. I didn't quite expect this amount of variability and also high sediment loads, but it shows you that if this lake is used as a reservoir for drinking water, that this is something that's very important for you to understand and to know, is the variability of water quality. So this one parameter is called total suspended matter. I want you to think of this as the sediment load in the lake. And if you think of it and you're looking at the water, higher levels of sediment will mean that the water will appear rather dirty and cloudy. It's full of material, and that sediment could be a number of things. And as the water gains clarity and the sediment settles, the water becomes generally cleaner. And if you can think, what you should think of is that the levels of total suspended matter are a proxy for water quality, because the suspended particles tend to hold a lot of the contaminants. So the more suspended particles you have in the water, the more potential for contaminants. So if you look at the left image, that's the maximum suspended matter over time, and you can see the portions of the lake where it's very high, and you can see the portions of the lake that are not so bad, like in the northwest region, that seem to be a little cleaner. But if you go and look at the image on the right, which is variability, this one I find quite interesting, and that is what portions of the lake change significantly over time. We know on the left-hand side where the max min areas are, But on the right, we get an idea of variability. And areas that are highly variable are going to be the ones in the dark colors. So this portion right here in the far southeast, that portion of lake is highly variable sediment load, and there's a portion up here highly variable. These areas here stay relatively clean and they're relatively stable. And this area here, though it's stable, it's relatively high sediment. So if you are going to monitor the water quality in this lake, images like this will give you an idea of where you might want to take samples and where you might want to pay attention to the loads, the water loads. So I'm going to move now into something called coastal change. If you're looking along the coast, and I'm going to show you an example later for Tanzania along the coast near Dar es Salaam, this is an area here, an example in Eastern Europe, where they were looking at 11 years of development along the coast, where they were developing a port for shipping, and they also saw in other areas where the land had been removed and degraded, coastal erosion. So areas that you see in red are coastal erosion, like you see down here in Kolovai. An area here in green is actually where they've increased the coast, so the water has turned to land. And in this particular area, they were building up the coastline and creating a port. And you can see another area here of coastal erosion where things have changed over time. I'll show you how to look at that in more detail for yours. So this is an example of urbanization. I did this example over Freetown in Sierra Leone. It's an area where we had some population data, so it allowed us to make some really interesting correlations. And this is done not, it's not done very cleanly with the user interface. There's a little bit more potential in doing this with a Jupyter notebook. But what you can see on the left is the year 2000, and on the right, 2017. And you can see this is the red areas are urbanized land, and you can see the significant increase in urbanized area. And this particular area grew 11.5% over 10 years. And we used an index here called the Normalized Difference Buildup Index. I also like to use something called fractional cover. I think does an even better job. So let me show you an example here. And this is a new product that we're working on that directly attacks the United Nations Sustainable Development Goal 11.3.1, which is a measure of urbanization. And so what we've done here is look at that same area, Sierra Leone, along the coast. We cropped out the lower portion, and basically we used a shapefile to crop just the region we want. And we calculated the urban growth to be 4.8% between 2005 and 2015. We know that the population growth for the same exact time period was 3% per year. And we got that data from GPW v4, which is a public global data set for population. And if you take the ratio of those two products, the urban growth to the population growth, you get a number greater than 1. And so what does that tell us? It tells us that people are rapidly moving out of the cities. They're taking over more land. So the population, or the urban extent of the area, is growing faster than the population is growing, which means people are taking over the land at a rapid pace, faster than the actual numbers are growing. And so this kind of information is important to know, because the opposite effect would be if population was growing and urban extent was not building, you would have denser populations in the cities, which puts pressure and stress on natural resources in the highly urban areas. In this particular case, you're expanding. This area has a lot of deforestation and a lot of expansion. but they're taking over land, and they need to understand, do they have the natural resources to sustain all that? So here's an area, another example for forest. So again, I wanted to use some examples for Tanzania. I don't know if I'm saying this right, but Usingi Forest in western Tanzania. This is an area of known deforestation. So this United Nations Sustainable Development Goal, its objective is to look at forest loss. And the way we did this is with a really simple approach called NDVI threshold. So basically, we're looking at the normalized difference vegetation index, which tomorrow I'll show you in part of the training what NDVI looks like. And if you threshold this, which means I basically take the NDVI values and I say any value between 0.6 and 0.9 is dense vegetation. And if I notice that the dense vegetation mask changes from one year to the next, I might assume that a highly devegetated area is likely deforestation. And in this particular case, there's two products you're seeing here. Number one is the data cube results on the left. And so everything in red on the left-hand side of the left image is an area that has been devegetated, and it's likely deforestation over a 10-year period. There was a difference there, or a loss of 10.6% in the land. The image on the right is a comparison product that's available on the web, and it's called the Global Forest Watch. If you Google Global Forest Watch, you can actually go find this. The person that creates this Global Forest Watch does not advertise their algorithm, so it's not open source. You'll never know how they do it. But for comparison purposes, I think you'll agree with me that the product that we have on the left with the data cube matches their product on the right quite nicely. So you could do a really good job of measuring the deforestation or the devegetation just with some simple NDVI comparisons. Getting near the end here, here's a few examples. These are not available in the user interface, but just to show you the power of some things that can be done for croplands and agriculture, we have a Jupyter notebook that looks at a particular area, and it puts all of the NDVI values into bins by monthly time. So if you think about, if I take an area, a vegetated area like a cropland, and I look at the time history of the cropland and I bin it up by month, what you will start to see is the cycle of growth of that cropland. And agriculture people will use this kind of information to study what's called the phenology, which is the changes in the growth patterns. So you can see things like the start of the season, this is the peak of the season, this is the cropping period of time or end of season, and then you have your cold season where you're back, and then here is planting again. This is a really interesting cycle. You see the vegetation reaches a peak here of the mean around 0.6, down of a minimum about 0.2, and a really nice cropping cycle. So I did these here. What you're looking at is really, it's what's called a box and whisker plot, and you get a lot of spurious data. You might get some pieces of really high NDVI, a few low ones, but notice the large chunk of data, or the middle quartiles, are grouped really nicely. Now, what if you do that over multiple years and spread it out? So this chart right here has binned up all the months over multiple years, but what if you spread it out over time? This is what it looks like. So if it's spread out over time, you see some really interesting things. First off, you see the lack of data during the rainy season. Notice there's a gap here. Notice there's a gap here. Those are the rainy seasons where you have a lot of clouds, and this particular field did not allow you to get any good data. So if you just curve fit this, you can still get a reasonable idea of what's happening. Notice the density of the data changes in 2013. In 2013, there's a lot more data here. Well, that's because prior to 2013, there was only one Landsat mission. Landsat 8 was launched in 2013, and now suddenly this is showing 2 missions gathering vegetation index data. So these are the kind of things that you can get. And lastly, I want to talk about where we're going with all of this in the future. I mentioned some of this in the beginning. We're planning to add Sentinel data, Sentinel-1, which is radar, Sentinel-2, which is optical data, very similar to Landsat, and then the ALOS data, which is a L-band radar data. We hope that that's going to be easier to add. We're hoping to get all this data into the cube for you in early 2019, hopefully build a few simple products on top of that so that the user interface can tap into it as well. We know there's been a number of problems with the African Regional Data Cube, the operations and the scaling of the cloud resources. We've run into a number of issues with the user interface. We've had some issues with the memory and running larger jobs if we're just doing Jupyter notebooks. So we are constantly trying to understand these issues, accommodate more users, and improve performance. It's not perfect, so I ask that that all of you are patient in moving this along and moving this forward. We're learning as we go. We're trying to figure this out and accommodate the users and their needs. And we have to figure out how to best scale this because we don't have a supercomputer like Australia. We don't have a huge computing cluster like Switzerland. They've got a lot more power available to them, but we're utilizing this thing called the Amazon cloud. And so in order to control expenses and yet optimize performance, it takes some testing and it takes some trial and error, and that's what we're doing. I wanted to mention that GPSTD, the global partnership, is hiring a new technical lead. We expect that person to be available in the next couple months, and they'll be able to help support the African Regional Data Cube. So there'll be a person that will be a more regular contact for you to help resolve things and also help with some face-to-face interaction. We're going to be developing an application library to share the latest algorithms. What we have now is a bit disorganized. We have a number of algorithms, but we need to get them in a more organized location so you know what are the latest algorithms, some documentation to go along with them. And so we're working on that. And we're also going to organize our learning center so that training products like tutorials and videos and case studies will be more easily attainable. So I'll end there and thank you for hearing this intro. I think it's important for those people that have not heard much about the African Regional Data Cube to get an idea of what it is, what products can be generated, what some of the challenges are, and so that there's a better understanding of all moving forward. And so we've got a Twitter account, we've got a website for the Open Data Cube, but we'll stop there. So I'll stop there with some and allow some time for some questions before we move forward. So are there any questions from anyone out there? This would be a good time.
Okay, Mr. Brad, first of all, I thank you very much and congratulate you for your good presentation. My name is Yathman Mshua from Tanzania. You talked, hello?
Yes, I can hear you just
Brad?
fine. Yes, I can hear you fine. Thank you for that, that bit of thanks, and go ahead with your question.
Okay, in your presentation, you talked about the total suspended matter. Will you please talk more about that?
Sure. So it was back, let me just get to it so we can look at it. Yeah, this is it here. Yes, this was in Manyara. So total suspended matter, what we do is total suspended matter is a proxy for water quality. It's not a direct measurement of water quality. I say it's a proxy because when you're looking at water from space, you have a limited number of spectral bands in the satellite that allow you to look at the water and distinguish and try to determine the level of water quality. So in the case of Landsat, you're limited to red, green, blue, shortwave infrared 1 and 2, and a near infrared band. So you only have 6 bands of information. And those pieces of information, one of those bands, I think it's the blue band, there is some literature out there that has developed an algorithm. They've tested this in Australia, and I can send you the paper that goes with this. There's a paper out there on this, and they tested an algorithm for total suspended matter, which is a measure of the sediment in the water. So what happens is the blue spectral band changes. What you see from space changes as the sediment load varies. And so that's what you're looking at here. It's a fairly simple algorithm. It's just a power law that is a proxy total. The reason I say it's a proxy is that many scientists will argue that the actual number here, so like whether this is 140, 80, 140 grams per liter of sediment, it's very difficult to know exactly what that is unless you do calibration and validation of that data locally in this lake to understand how does the sediment load vary according to what the satellite is seeing. And so if you were to do an analysis, a ground validation analysis, you might be able to find the actual numbers related to the satellite data. But what I suggest is that using this parameter, total suspended matter, it does allow you to see the variations within the lake spatially and the variations in time. And so that's the more important thing here is if you've got a time series stack of data, you want to be able to see variations in space and time. And so this is time and space variability. This is really spatial variability because it's just looking at what's the maximum over the entire time period. And this one is showing the variability in time over that window. So I don't know if I answered your question. I can certainly send you the paper that talks about total suspended matter and how it's measured in the algorithm we're using. And if you have any known algorithms, you might actually have some algorithms for chlorophyll or for CDOM. There are a number of algorithms out there, but there's also a lot of discussion within the science community about the accuracy of those algorithms using the Landsat mission. Not many scientists are convinced that Landsat does a great job of water quality measurements. Sentinel-2, when we get the Sentinel-2 data in there, I believe it will be better because it has more bands and more information. But with the limited data we have in Landsat, this is pretty valuable information. It certainly gives you something to start with and get an idea of variability. So let me know if you have, is there another question you have in particular, or did that help?
Okay, thank you. Another question? Another question, please? Here in Tanzania, there is no question.
No more? Okay.
Brad?
Yes.
No more question.
Okay, great. So I'm going to move over now to do a demonstration here on the user interface. So I'm going to request that nobody jump on this website while I'm demoing so that we can watch my demonstration, because if anybody else is trying to run a case while I'm simultaneously doing this, it's just going to slow down because we're sharing the same resource. When I'm done this demo today, and you have an opportunity to go to this website. Yes.
Brad?
Sure, go ahead.
We don't hear you properly. I don't know what's the problem.
Can you hear me now? Is it okay?
We don't hear you properly. Maybe there's something wrong.
Yeah, maybe.
Yeah, sure.
How about anybody else out there? How about my team? Andrew, Syed, Sanjay, can you guys hear me okay?
Yes, we can hear you.
So maybe there's an audio issue on the far side. If there's any feedback, if you're hearing any feedback, perhaps muting the microphones on the far side will help as well. I see there's a caller online, caller 3, that's not muted. I'll try and mute that one, and maybe that will help. All right, we'll see. So let me know if my audio doesn't work as well. So I'm going to first start by, I sent out a document that I'm going to show you here that walks through a DataCube tutorial, and I'm going to show you this tutorial now live. So I'm giving you the website, but I urge you, please don't go there until I'm done with this presentation so that I can have the resource of this website for this presentation, so things will run faster, because I'm going to do this live. If I run into some issues and it's not running fast because people are on it, then I won't be able to demonstrate it nicely. So later on, when I'm done, please visit this website, and I have shown you in the document a few case studies of water detection. I'm going to show you one here, a really interesting reservoir, the Matera Reservoir just south of Dodoma. Really interesting. I'm going to show you that one. I'm going to show you how to probe within that reservoir and look at time changes. I'm going to show you total suspended matter of that reservoir, water quality, and I'm also going to show you coastal change out near Dar es Salaam. So here's what it looks like when you get to the user interface. I'm just going to, so here's what the user interface looks like when you arrive. So when you arrive, the first time you try to log in, it'll ask you to register, and you'll just register your own username to jump in. It just asks for an email address, so you'll have your own username, password to log in. That's just so we keep track of who's using it. We're not sending out emails or spamming you with anything. When you get here, this is the home page at this point. DataCube Manager gives you a few ways to look at what cubes are out there. So if I look at DataCube visualization, it shows here are the 5 data cubes. You see Tanzania is the largest. If I click on the Tanzania block, it shows me that I have Landsat 7 data. There's the extent of the Landsat 7 data. And there's the extent of the Landsat 8 cube. It gives me the years. It gives me the number of scenes and everything that's in there. So what's interesting, if you go back and you look at the Landsat 7 data, there are 9,340 scenes in this cube of yours, which is a lot of data, a tremendous amount of data. So it's really impressive what's in here. So I don't use DataCube Manager very much, other than to just see what cubes are out there in this tool is connected to. The one I use more often is the tools. So that's what I'm going to show you here. There's an area here for Task Manager when tasks are running or how to submit feedback. I won't cover those today, but you can take a look at those. Submitting feedback, if you have issues, you can email us. But I'm going to start here today with water. And so there's, under the water tab, there's 3 different things that can be run: water detection, water quality, and coastal change. We're going to do them in order. And let's start with water detection. So the first thing I do when I click on this is I have the cubes that are available to me, and I'm going to jump on the Tanzania cube. When I zoom in, please don't run things that large. They will not run. There's limitations. The limitation, I believe, is about a 1 degree by 1 degree tile size. Try to keep things small. I promise you they'll run better. So if you start really small with your analyses, get an idea of how fast that they run for you, then you'll be able to expand from there. So I'm zooming in just south of, here's Dodoma, here's Lake Salunga, and just south of Dodoma is this Matera Reservoir. So this reservoir here is quite interesting and has had a lot of variability. And what I'm going to do is I'm going to pick a portion right here, and I'm going to run a water detection analysis. I'm going to run it for the entire 17-year time period. So you can pick the start date and end date, and I chose my region by clicking in the top left and dragging. You can put a lat long bounding box by hand if you desire, just by putting it in these windows, and you can pick a different start date and end date. That's entirely up to you. I'm just running here Landsat 7. I'll show you how to run Landsat 8. And notice the water detection query is running right now, and it shows you the run progress. Now, I want you to think about this and be patient in a sense that this is taking 17 years of data for a decent sized reservoir, analyzing the water extent over all of this time in 17 years, looking through thousands of images. And so there's a lot of data underlying this query. But in a moment, it'll be done, and we'll see the product on the screen. And the product, when it's done, we'll just go there to show you what it's going to look like. It's going to look like this when it's done. And what you're going to see when it's done is this colorful picture that represents, remember, anything in dark blue is water 100% of the time. These areas here were not water all of the time, and the areas in red are extreme events that might have only been underwater for a period of maybe 1 time or 2 times in 17 years. So this variability can be very interesting. What's interesting about this reservoir is this is the only portion of the reservoir that has maintained its constant water state in 17 years. So our task looks like it's done, and I'm going to go back and look at it. So how long did that take? That took probably a minute to a minute and a half. Again, you got to be patient to do these tasks. If there are 5 people running this task, the same task simultaneously, you're all sharing the resources, so it's going to multiply the time that it takes to run some cases. So you just have to be a little patient sometimes and recognize there might be others running. So let's zoom in and see what's happening here. In the top right corner is the legend. If I click on this little water droplet, that's my legend. And you see with the legend here, in the top is the normalized water percentage. That's what we're seeing on the screen. That's the default. Red is 0 to 5% of the time, and then the dark blue is all the time. So if I zoom in, what's happening here, it's a really interesting and colorful output. The entrance to this lake or this reservoir right here, there's water coming in from this river. Notice it's yellow, which means not even this river is water all of the time. So that's part of the reason why this lake is not fed, or this reservoir is not fed constantly, because this inlet here is not constant. So this area is small portion of time, yellow 5-10%, green 20 to 30%. So again, a lot of diversity in this lake. This portion here is water all the time. Well, what if we wanted to know about the history of what's happening here? And when did this little spot right here experience water? There's an eyedropper in the top left, and this is a pixel drilling tool. And if I click on this, it allows me to locate a pixel drill, and I'm going to put it right here. And it says, wait while your plots are being generated. So I close that window and I wait, and this might take a minute. Oh, that actually was quite quick. Thank you, Andrew. Awesome job. It ran very rapidly. So here's what happens. This particular pixel that I zoomed in on, notice it tells you the precise lat-long position. What has happened in the history is shown in these two plots here. Let's look at the one on the bottom first. The one on the bottom is a mask that is a cloud mask. We probably might want to change the title here, but basically it's telling me the difference between cloud and clear. If it's 1.0 clear, that's 100% clear. That means these are good clear scenes. So not a lot of clouds. The dots that you see on the bottom are scenes or time periods where there were clouds. So this is a fairly clear area because you're getting a lot of data. The plot on the top is the one I find the most interesting. This is water, non-water. This particular pixel right here that I drilled down on had only experienced water in about the time period of 2008. The rest of that 17-year cycle, there was no water. So what you see here is no water, water for about a period of maybe 6 months, and then no water again. So let's zoom out and let's look at a different location. So what if I come over here and look at an area in the middle of the lake with a little more variability? So again, I click on the pixel tool and I zoom into this area here in light blue, and let's see what it looks like here. So again, this is not water all of the time, but in a moment when it comes up, you're going to see the variability, and here it is. So notice again, it's not very cloudy. I get a lot of clear scenes. Sometimes you'll see a lot of cloudy scenes and very few clear. But let's look at the top, the water, non-water. What you're seeing here is that this particular area here was water. It was non-water for one little time in 2002, but mostly water all the time. Then there was a dry period around 2005 or 2006. Now, if you remember in the Lake Manyara image, I said there was a drought around 2005 or 6. This is about the same time as that drought period. So that drought might have existed around much of Tanzania. So there's a big dry period. The water then existed again, another fairly large dry period in 2012 to 14. And now, since 2016, it's wet again in this location. So it's really quite interesting. You can see all this variability in these plots. I'm going to move this over and look again at some of the water history here. So if you wanted to use a map like this for flood risk, you can really look at some interesting things. So let's say if I just did a new analysis in Dodoma and said, I'm interested in a portion of Dodoma where maybe there's been some flooding out here. This is the University of Dodoma, and I'm going to submit a job here to run over University of Dodoma, and just look at these areas here. I see there's probably some ponds here. This is the university system, and let's see what the time history of water is around this university area. We'll let this run. I'm going to go back to my plot here. So again, I ran a larger one last night that I did all of this. It's really complex down here. It's pretty interesting in the bottom. And these are some examples of the pixel drill. And next I'm going to go into the water quality. So this case ran. So look, what's interesting here is that there's hardly anything. So this was a university in the middle. Basically, in 17 years, none of this area has ever seen was any flood prone, but there's a little spot over here on the far right. It looks like next to a little lake. But if I wanted to click on this and see this little red spot when it experienced water, I can click on this and we'll wait for a moment. It will plot and we can get an idea of when did this particular area experience water, the one area that was shown in red. It's taking a little longer this time to plot up. I thought I did it, maybe not. Oh, there it is. That particular area, which was just to the far west of, or far east, only experienced water one time in 2015, somewhere in 2015. So was probably a heavy rain event. Water was settled there for a portion of time, and one of the Landsat scenes picked it up. So one time in a 17-year time window. So I'm now going to go back and look at some of these scenes and look at some of the details of what's happened. So there's a few tabs along the top that tell you what jobs that you're running and a little bit about the tasks that you ran. If I go to the history is going to show me all of the different jobs that I have been running as I'm logged in here as KILO. And you see I ran a bunch of jobs last night. I looked at a single scene. I ran a whole bunch of these jobs, and it keeps a history of the jobs that I ran. If I go to the results tab, it shows me the jobs that I've been running since I last logged in, which was just here this morning. I ran 2 jobs. I ran this query here. There it is. And I ran this query here, which was that one. And so you can jump back and forth between the 2 queries, and it gives you information about the job that you ran. It shows you the time that it's submitted. You see that it took about 2 minutes to run. The latitude, longitude, showed me the water observations. Now there's another thing that can show you, there's a couple other products. This one is called water observations. And if you look at the legend, this is the number of water observations divided by the maximum observations, which is a bit different than the number of clear observations. Because this one sifts out the scenes that are not cloudy. This one says the maximum observations, including the times that it was cloudy. So you get a little different view. And if I look here at show clear observations, that's just going to show the cloudiness. And basically what it shows is I've got a lot of clarity here. I'm losing some scenes and some cloudiness over here. But that's the main product we normally look at. I can also look in the results tab and I can load individual scenes. So if I wanted to look at what does the water extent look like on December 17th, 2016, it was 86% clean pixels, so there was some clouds in the image. I can load that individual scene. I click load scene, and what this is doing now is it's going out and it's retrieving that single acquisition, and here it is. So all this is showing me is the extent of the water for that one particular day. So notice what you get. These little bands are the Landsat 7 bands that unfortunately mess up the data a bit. Well, remember we saw back in 2005 or 6 that this reservoir was much smaller. If I went into the results tab and, oh, wrong one. Go back to this one. And I wanted to look at the results tab back in 2000. There's a lot of scenes here. Matter of fact, quite a few. There's the scene count, 206 time slices. If I go all the way back to 2005 or 6, this is when I knew the area was very dry. Here is, we'll do this one here, which is September 2005, and I load that scene. Watch the difference in the size of the reservoir in 2005 and notice what it's done. So this was a big difference between the two results that I just showed you. So again, I can go back to the results tab. There's the result here. I can show this one. I think there it is there. That's the full reservoir. Or if I wanted to look at the single scene for 2005, there it is. So there's the bigger one. So you can go back and forth between them. There's 2016, there's 2005. Difference in the water. So you can do this at any point around Tanzania. Using the results tab, you can look at individual layers. Using the, you can also look at the total products here, which is the total water percentage. And then finally in the output tab, if I wanted to wipe out any of these, I can go to these and look at any of these output products, and I can pull out that product. So let's say, I think it was this one. Nope, wrong one again. If I wanted to take this output product and I wanted to pull it out for viewing elsewhere, I can click on the output product, which I've done here. I go down to download selected and I can pick out what I desire. I can output the water percentage and download this. And if I click download select, it's going to download a PNG file to my screen. So I can use that then in a presentation or something like that. But what if I wanted more power? I could download the GeoTIFF product. And if I clicked on that and hit download selected, it'll start downloading a much larger product, which is a GeoTIFF, that you can then go use in a GIS tool. So if you looked at that water PNG file and I go to my desktop, there it is right there. So the file's been downloaded to my desktop. It's a nice resolution file, but it gives you an idea of what you can do. So if I go to the results tab, I can wipe out some of these by deleting them. I can come down and delete this one. I can delete this one. And I can delete this one. And now I'm back to a clean product. I have nothing that I'm running at this point. So, cancel that one. So now I am back to where I was in the beginning. I want to show you now water quality. So again, we were looking at how do I produce images that look like this, which is water quality, and I'm going to show you how to do that. So let's go again back to this same reservoir, and I'm going to look at a Landsat 8 image of water quality for this reservoir. Remember, the portion of the reservoir that's constant water is this part here. But Landsat 7 or Landsat 8, you can pick at the top. If I pick Landsat 8, notice what happens. The time window changes from 2013 to 16 because that's the only time it was available. But we're going to be giving you more data here. This should go through 2018 pretty soon. I'm only going to run Landsat 8. I'm going to run this area here. And I'm going to, I take that back. I need to run water quality. Let's do that again. You have to pick up water quality tool. I have to pick that tool up first before I run the analysis. Now I'm back to the reservoir. I'm going to choose Landsat 8. I'm going to choose a result type. I can take the average total suspended matter, the minimum, the maximum, or the variability. Let's look at the average. I do the average. I'm going to run it for the whole time window, and I'm going to do that, and I hit submit. So again, this is only querying about 4 years worth of data for Landsat 8, and it's calculating the total suspended matter using that algorithm. And in the end, it's going to give me a product that will show me the average total suspended matter for that 4-year time period over this portion of the reservoir. So give this a moment here. When it's done, your product is going to look like this one right here, because I've already run it once. And so you'll get this colorful product here. And this product for average total suspended matter, remember the range. Darker colors are higher sediment load, lighter colors are less. So if this was really clean water with low sediments, you'd get these blues and greens. There's not a lot here. The average for this reservoir is pretty high in this region. There's quite a bit of sediment load in here. So it just tells you it could be from rainwater and runoff. There's a number of things that drive the sediment loads high. But this is still running. And when it's done, we're going to look at a product that's going to look like this, and I'll do a pixel drill and show you what that gives you. This pixel drill that I did right here, when I come down, it's going to give me a plot that looks something like this for total suspended matter over time, and I'll show you that in a moment. So again, you have to be patient. Again, I told you some of these cases, this is just a fairly small window. It might take a few minutes to run. So this is average TSM. Here you go. And this is the average. This is not min or max. I think it's possible that what was shown back here, I think this is the maximum. Oh no, this was TSM variability. So that was variability. I'm just plotting the average here. So I plot this average, but what if I wanted to know about this portion of the lake over here? I could click on the pixel level drill and I click on that portion of the lake, because maybe that portion of the lake is an area that I have taken a water sample over time. And let's look at the plot. So on the right-hand side, again, this is the area we're zooming in on right here. Here's the data that you get out. The bottom one is clouds and no clouds. So this is the clear mask, and this is the clouds, plenty of clear scenes. This is the water, non-water. There's only one little chunk of time it wasn't water, but this little thing was water almost all the time. And notice the variability in total suspended matter. This looks like a lot of seasonal variability is happening in this part of the lake. So what's happening is at certain times of the year, the total suspended matter is lower, the water is cleaner. Other times of the year, it's increasing back to lower suspended matter. Increased was fairly high here in a period just prior to the drought. Then it dropped off, we lost water, and it's maintained an area here fairly high. But you can do this at any point in the lake. So let's say I clicked here and I went down into a different portion, maybe this spot right here. This is a reservoir. So again, I'm looking at the variation in total suspended matter at that portion of the reservoir. Notice this one, fairly low sediment loads. The only peak here occurred in about early in 2016, but you can see that's a fairly stable sediment load at that portion of the reservoir as opposed to others. So again, this is just a demonstration of what you can do with total suspended matter. I can run this in other places. I can run this in Lake Salunga. I can run this in other spots throughout. So just to let you know, there's some issues we have with Lake Manyara, where some of the data here is not properly connected to the cube. I think it's a Landsat 7 problem, not a Landsat 8. So if you're running some analyses with Lake Manyara and you run into some issues, you might want to use the Kenya cube, because it's interesting, but the Kenya cube, because it's on the border, actually overlapped, and it does some of these areas up here are part of the Kenya cube. We're going to fix this problem, but just to let you know, in the northern parts of Tanzania, if you're running some cases like near Mwanza or here, you might see some issues. If you see any issues, jump over to the Kenya cube and it should run better, because the Kenya cube. I'll show you as an example. If I go to water detection and I choose Kenya, notice that the lower portion of the Kenya cube includes Lake Manyara and a portion of Lake Victoria. So the Kenya cube, because of the overlap, allows you to run without problems. So finally, let me go look at coastal change. So we'll do coastal change in Tanzania, and I'm going to go look at an area here in Dar es Salaam. So we'll zoom way in here in your city, and let's look at this inlet right here. And I'm going to run a case here where I pick a spot like that. So I'm going to be looking at what's happening along this coastline here. And I'm going to run, I'll start, you have to pick a beginning year and an end year. I'll choose 2005 to 2015. So we'll do a 10-year time window, and we'll look at what has happened to the coastal change over this 10-year time window. We'll let that run. So let's look and see what that product looks like, because I ran some cases. That ran very quickly. But in the end, you're going to get things that look like this. So let's go back and look and see that there's two products. Well, there's certainly some problems in here due to some clouds and some areas that are masked out. I'm going to go over to the output tab, or actually the results tab. And in the results tab, I can change between viewing the coastline change. There's two different things. This one is the red-green coastal change, and this is the coastline shift. I usually toggle between the two. Let me rerun this case just for clarity, because there's some cloud issues in here. Let me go 2002 to 2016 and rerun that, because it looks like in 2005 and 2015, there were a lot of clouds and some missing data, so not a lot was visible. You tend to get some of this problem. Okay, here's much better. So it's a lot clearer, 2002 to 2016. So let's first look at what this is telling us, the green and the blue. There's a significant amount of coastline change that's happening right here. And if I go to the top right, I can look at the legend. The legend, the first thing that's shown to you is this top product called coastal boundary. The old coastline is in green. The new coastline is in blue, and you can see it along here. This is an area here that was probably a sandy coastal area, quite large, and that was completely lost between 2002 and 2016 because the new coastline is close by right here. Not sure what this was, but this area now has turned to water. This is just outside of Dar es Salaam along the coast, and that's an area you see here. If you go over here, you can see some changes also where the coastline has shifted. Well, each one of these pixels is 30 meters, so there's a lot of shift. There's hundreds of meters of coastline change here. Well, let's go look at that product in a different way. I'm going to look at this last query. I'm going to show coastal change in colors, which is this one. If something has changed from land to water, it's in red. If it's gone from water to land, it's in green. And notice what you see here. This is the receding coastline here. This could have been done on purpose, or this could have been done through natural causes, but there's a significant amount of coastal change here at the inlet. Notice what's happening out here. This particular area went from water to land. So this particular area looks like an offshore reef of some sort, or perhaps a man-made island or a protective zone. Maybe it was a man-made reef, but this area did not exist in the beginning of the time series in 2002, but later in 2016, this is land. So you can start to see these changes between this area here, turned to water, this area here, increased coastline, and you can run that in many places along the coast to look at these changes. So again, I'll go back just to show you, I ran a case here. I think this was 2000 to 2015, where I was looking at some areas. And you can just start to see these changes from beginning to end along the coast. You can also do this with inland water bodies if you wanted to see how the reservoir has changed with time between two time periods. There's a number of things that could be done. So remember, we were looking at that prior reservoir that had a significant change between 2 years. You could also use this. So with that, I'm going to end there. I'll just go back to my home page here, and I will open it up for any questions. And I appreciate all of you refraining from using the user interface while I was using it, because things ran fairly nicely. I will say that after this demonstration today, I would love for all of you to go give this a try and test out the user interface, try to produce some products on your own, and tell us what you think. Let us know if there's any issues or things that you run across. So I'll end there and see if there's any questions. That's basically all I had for today. Thanks. Any questions on from the Tanzania team?
Oh, Mr. Brad.
Yes.
First of all, congratulations for your good presentation.
Thank you.
Okay, another question?
A very simple question. How are you, Brad?
Good. How are you?
I have a very simple question.
Sure.
What is the difference? I'm good. Can you please explain a little bit the difference between land to water area and flood areas? How does it relate between the land to water and flood areas?
And flood areas. Right. So, yes. So what happens is this. So there's two tools, right? There's two tools you can look at to think about water risk or water flooding. So let's go back and look at them. One is coastal change and one is water detection. So if I'm thinking about, let's run the water detection. Remember, I ran the water detection area over here, and I ran a little case here over time, and I showed that there was some variation in this reservoir in that location. But that is one indication of flooding, because I can see the time history of water in this location, and I can look at that, the percent of time that any one of these pixels have witnessed water. But another way we look at things is this coastal change. The way we run this, it's a little, I'm trying to figure out a better way to describe it. What we do is we look at two different periods in time for this product, and we only compare, did the pixel experience water or land in the beginning time period, and did the pixel experience water or land at the end time period? And that is how we get this piece right here, land to water, water to land. So I believe that, let's see if we can force it to do something here. If I think it was right here, this was drying out. Let me try something really quick. There was a portion of this reservoir that was drying out, and I forget the time period. Back in 2005 and 6, this area was dry. I think if I go to this one here in the green, just try something a second. All right, yeah, so it's very dry in 2006. So if I take 2005 and compare it to 2016, for this spot here, I might get something. So let me show you. If I go to coastal change, now again, this is not really a coast that we're dealing with, but I want to show you the difference in these two products. I was able to look at this little location here, and I compare 2005 to 2016. I'm going to now see areas that land to water, water to land, and this is what I get. So these pixels in green, let's go, let me get I like to look at that product right here. These pixels in red are pixels that have changed from land to water. So these pixels were dry in 2005 and became water in 2016. So they went land to water, water to land. So that's what that's telling me. Let's run this for the entire area. I'm going to run a bigger one. So let me do this. So you can use the same coastal change product for an inland water body, but you're only comparing 2 years. So if I just look at 2005 to 2016, I'm only comparing 2 years here. That's what the coastal change product gives you. The other product that we had, which was the water detection, it's looking at all the years and all the time slices. So I'm doing here just 2005 to 2016 to show you that much of this reservoir in 2005 was dry, but in 2016 it filled up. So here it is. And again, the product I like to use, I go to the results tab and I turn on the show coastal change. There's the product. So what this says is areas that were land in, if I go back to my filter, remember it was 2005 to 2016. The areas in red were land in 2005 and became water in 2016. So this is all water in 2016. And so you can see the expansion. This area here didn't change. So it doesn't get any color if it doesn't change. And I don't see any green in this photo, or this image. So it's telling me that this inland water body, there was nothing that went from water to land. This only went from land to water. So water to land would be a different one. So I think if we rerun this for 2000 to 2005, we should probably get just the opposite, because I think this area dried out in 2005 and then the water came back afterwards. So let's look at 2000 to 2005. First thing it does is plot that. I go to my results tab and I like to change the results and show the show coastal change and look at the difference. Notice it's green. Well, if it's green between the year, here it is here, 2000 and 2005, everything in green went from, went from water to land. So this area here was water in 2000 and went to land in 2005. So this is the portion of the lake that completely dried out from 2000 to 2005. So pretty interesting. So again, we could look at this. You could look at this for other lakes and try this out. So I guess to answer your question, I'm sorry I've gone a little long on this. There's 2 products you can work on: water detection, which looks at all the time slices over time, and coastal change just compares 2 time periods, compares 1 year to another year and looks at the change. So for an inland water body, this is pretty powerful because it'll put colors to changes, areas that have increased or areas that have decreased comparing 2 years. So I hope that answers your question. If not, let me know, or if you have, I could work with you offline to answer any other questions. So was that clear? You can get some really interesting stuff if you run the coastal change product on an inland water body. You get some pretty interesting results. Are there any other questions out there? While we're running here, I'll go up and run Manyara. I think it'll run for the Landsat 8. I think I can do it for Landsat 8. So I think I can compare 13 to 16. See if it runs. Any other questions out there?
I think there is not any other question, but I think what I wanted also, of course, not a question, maybe next time when we come back, I was thinking that if we can use this tool to detect some of the places or some of the areas whereby maybe during the rain season, and then could come like flood areas and definitely cause some of death among people. And then if we can identify these areas early, and then it's now to communicate to our people, to the people that they should vacate in those particular areas before the rainy season begin.
Exactly. Yeah, that is a definite. This tool here, water detection, will give you just that. Is there a particular area? I can just do a quick little example for you right now. Is there a particular city or region? Is it near Dodoma or one of the other larger cities?
In Dar es Salaam.
Dar es Salaam. Okay. So let's go to Dar es Salaam. So again, the tool I'm using is water detection. So I'm near Dar es Salaam. And let's say there's a portion of Dar es Salaam, and because I see there's a lot of interesting little water areas. So let's say just north of Dar es Salaam, and I'm looking at this village here, Makongo, and I want to look at the water history around Makongo here. And I'm going to run the whole time series, 1999 through 2016, and just let's look at the whole thing. Because this is going to give me 17 years of information, and it'll give me a good idea of what's happening around this area. Did any portion of this area experience some abnormal flooding? Or is it just, or the rainy season type flooding? So here's what you get. Very interesting, because remember, red is a very infrequent 0 to 5%. I will bet you these red spots are only one period in time. And you can go to the results tab. If I click on the results tab and I toggle it off and on, it allows you to see if I get this, show hide. Oh, I think that's it, show hide. I can go back and forth, show hide, because I might be zooming in on a little town here, and I say, all right, I know this little town right here. I can show hide. It's never, so this little block right here, let's say I was looking at this little area, it's never experienced water in 17 years. But how about an area down here? This little area right here, that area right here was water. So this spot right here near Kimba Road, let's zoom in a little further. That area here, I do show hide. That area right there was red. Do you see that spot's red? So I'm now going to figure out when was this experienced water. I use the eyedropper tool and I click right there. And this could be somebody's house, or this could be a village. I click on that and I wait for a moment to see when over 17 years did this area experience water. And again, it's only one flood event, so I wouldn't be as worried about this one. Some of the areas that are yellow or green are areas that are going to be seasonal flooding. Let's wait a moment here. This is generating. I'll zoom back out. It's taking a moment to plot up. All right, I'm still waiting for it here. We'll see. If it doesn't show up, I'll go to a different spot, and I'm going to try and find an area that has more significant flooding. Possibly down here in this area, which is near the water inlet. Yeah, it doesn't seem to be coming up that quick. So let's go down. I'm going to run a little case down here near this water inlet, and there's a military base down here, and these are wetlands. So these areas that, yes, sir. Go ahead.
Yeah. Can you identify an area called Msimbazi River? I think that is the place whereby most of the time we always suffer from floods during the rainy
I see
season.
it right here. It's this one. Mzambi River? Msimbazi?
Msimbazi. Yes.
All right, here it is, right here. So here's the river. It comes in here and goes through. There's the river right there. So let's go along this river, and let's say I run a case right here. Here's the river, all along here. And I'm not sure where it causes more problems, but let's run an analysis case here over this portion of the river. And I'll go back to my filter, and I will run it for 17 years. So we'll see. So again, see the river runs through the middle of this. And you can see the roads and towns, and there's a map in the background. But let's see if this, quite interesting, right? Experienced a bit. There's a water plant over here I can see. A water. So look at this area in yellow. If I go to the results tab, and I do a show hide, and I zoom in on this area right here in yellow, this area right here, and this is a portion of the river. So this area right here must get a good bit of water because it's yellow. And so I can click on this and, alert, this field is required. I'm not sure why. Yeah, there it is. Plots are being generated. So we're trying to generate a plot for the time history of this spot in yellow along that river, and here's what you get. Very interesting in that this location here, and we can toggle in and out on the map and see what particular area this is, experienced water in 2006, looks like in 2009 twice, nothing again in 2014 and maybe 2015. So this little area here 5 times in 17 years had water. So this area in yellow is a little more frequent than the areas in red. The areas in red are very infrequent. So you'd have to do a larger region, and maybe if we did a spot, let's see if I did something like I ran all of this. I know that this river runs right through the middle of this scene. If I ran a much larger spot, let's see if this one runs rapidly. What I'm trying to find are these seasonal rain situation that you're talking about, which are going to show up as usually yellow or green in color, because if something occurs seasonally and it's pretty much every year, you're going to see 30 to 40% of the time. And so this was the old spot we were running here. There's a lot of water that stands at certain times of the year, but it's not that frequent. If you look down along here, along this river, along this spot here where this is green, and I click on that spot in green, I'll bet you that one has a more seasonal variation, or maybe it was just a particular period in time. Yeah, so what happened, look at this one. This has got seasonal water in it, but not starting till about 2007 or 8. So it was fairly dry up till 7 or 8, and then it looks like it goes wet, dry, wet, dry. This is some seasonal variation here for that particular spot. But you can see the complexity of everything here, and I can take a map like this, and I can go to the results tab, and I can toggle on and off the area, and I can find particular locations. So let's just say I do a show hide and I look at this area here, and it's plotting, whoops. If I wanted to see a particular village or location, I can look at this location here. So it looks like this area here has experienced flooding, but how often? Probably not. Oh, I've got to go back to the filters tab. And let's wait and see that particular spot. So there's not a lot, even just along that river you were mentioning, I don't see a lot of seasonal flooding that's significant. This particular spot here only experienced water one time in 2008. So anything in red, like you see here, very rare water extent. And we can start to do things. You can look at Landsat 8, which is more recent. And what we'll do is, as we add more data to this, and we add data for all the way through 2018, you'll be able to run these analyses for more recent time periods. So if you knew that this area had been flooded in more recent times in 2017 or 18, right now we're not going to be able to see that, but pretty soon we'll be able to add that. I think that's the inlet of that river right there coming in. So I hope that was helpful. Try to run some of these analyses around various places in your country. You'll see some areas that have seasonal rains and others that do not. It all becomes quite interesting if you run this in some areas that there's some areas down here which I think are wetlands. These areas in blue are wetlands. You start to get different kinds of products in wetlands because there's nobody living in these areas. Any other questions out there? But try this out. See what you're able to find on your own and probe around. Try to run. Remember, start small, and then increase the size and complexity of your analyses as you go, just to make sure that they're running rapidly for you. So are there any other questions? If not, we can end there. And tomorrow I'm going to show you how to create a cloud-free mosaic from this tool. So tomorrow we are going to look at general mosaics, and then we're going to look at the land spectral indices and a variety of these other tools. So we're going to look at these other two tabs tomorrow, and I'm going to walk you through some examples there. I think you'll find those interesting as well if you want to take some of these products and use them in your GIS tools. Any other questions today?
No, any more questions? We thank you very much for your time, Brian. And of course, what we have to do now, just to exercise by ourselves and then to see on whatever we are going to be stacking, we'll be coming back to you and of course, asking
Excellent.
how we can go through. But otherwise, thank you very much for your time. Then hope to see you tomorrow again.
Fantastic. And I might suggest, if you have a chance, I know it's late in your day there, maybe tomorrow morning your time, if you run any test cases and play around with it. If you have any questions or run into any issues, maybe we'll take the beginning of tomorrow's telecon to just talk about any issues you ran into or any things you discovered. It would be great. Or if you wanted to share some results with me tomorrow, that would be great as well. Thanks.
Thank you.
Well, have a good evening, everybody, and thanks again for your time.
Brian,
Yes.
how are we going to have this lecture that was given to us today? Have you recorded it somewhere?
Yes, I have recorded it, and I will make a YouTube link as soon as I'm done here and wrap this up. I will upload it to YouTube, and I'll send you the link shortly. So I owe you two things. I'll send you the link to the YouTube recording, and I will also send you that literature paper on the total suspended matter of the water quality. Okay?
Okay. Thank you.